Morning. I'm Nicole Testa-Boston. I'm the Deputy Director of the FIATech Consortium, and on behalf of all of us at FIATech, I want to thank you for joining us today. We have an exciting hour set aside to hear from Mario Burgess on his presentation towards energy-aware facilities inferring appliance-level consumption. He was awarded the SETI Award at the FIATech SETI Gala this past April in the Outstanding Early Career Researcher category. And in the next few months, we'll be featuring the recipients of that award, so you can all learn a little bit more about the work that they are doing. Before we get started, I just want to go over quickly for those of you who may be using GoToMeeting for the first time. That toolbar is unique to you, so you can minimize that and get that off your screen if you want an unobstructed view. We do have a setting where all of you are muted, and that's due to the number of attendees on this call. But we do encourage and welcome any questions, clarifications, points that you would like to make. Please do so using the questions tab on the toolbar. Those will go directly to me, and periodically throughout the presentation, Mario will stop and take those questions. I will read those to him. I will not indicate who is asking the question or from which company, so it will be anonymous, but we do encourage participation that way. I also want to mention that we will be recording this presentation, both the audio and the slides, and we will be making a copy of it available on the FIATech website at fiatech.org. It usually takes us a couple of days to get that packaged and loaded, but we will have that up hopefully by Friday. And so with that, I want to go ahead and introduce Professor Mario Burgess. He's with the Department of Civil and Environmental Engineering at Carnegie Mellon University in Pittsburgh, Pennsylvania. He's an assistant professor, and his research interests include infrastructure monitoring, building energy management, building technologies, machine learning for signal processing, and sensor networks. He received his Bachelor of Science in Civil Engineering in 2004 from the Technology Institute of Santo Domingo in the Dominican Republic, where he is from, and his Master's of Science and PhD in Civil and Environmental Engineering in 2007 and 2010, respectively, both from Carnegie Mellon University. So we are very pleased to have you with us today, and let me turn over the presentation to you now.
Thanks, Nicole. Thank you, and welcome everyone. So today I'm going to be talking about some of the work that I've been doing over the past couple of years. Specifically, so if you read the original title when the invitation was sent out, it was about monitoring infrastructure in general. But I'm going to be talking specifically about building energy monitoring and some of the work that I've been doing in that space on applying information technology to solve problems about monitoring electricity consumptions in buildings. So with that, I'd like to start always with the very broad picture and why, sort of the motivation of why we're doing this. So if you look at the energy consumption throughout the U.S., and I'll show you a quick picture of the whole world just to give you a sense of what that is. We are consuming here in the U.S. about 100 quadrillion BTUs of primary energy every year, and that's a figure for 2008. 40% of that is going to producing electricity, and of that, 73% is going to commercial and residential buildings. So we believe that there's a good opportunity for reducing consumption in this space, and that by doing so, we're actually contributing a lot to the larger goal of reducing energy of those 100 quadrillion BTUs of primary energy. So you ask that same question in another way, sort of thinking of how we're actually consuming that energy. So on the left here, we have all the sources of energy, and on the very right, we have where that energy is going. We can see that there's a lot of energy that is at the end either rejected because you're not using it effectively through the conversion process. It's being lost, converted to heat, or maybe you're just not using it at all. But if you look at that, in the middle we see the electricity generation. That's a very large chunk of that is being rejected. So during the conversion process of taking solar, nuclear, natural gas and coal and converting that to electricity, a big part of that is being lost because of inefficiencies in the conversion process. But as that blue bar, which is the actual energy that's used, increases because we are being more efficient at converting electricity, so will the residential, commercial, and industrial, and even the transportation sector now with more electric cars coming up, will increase. And so we think that there's a good opportunity for us to focus on not only how to make energy conversion more efficient, but also how to make use of that energy more efficiently so that we can reduce those numbers that are there. But what do we know right now? So if I ask you, owner of a building or owner of a home or renting a home, how much you are consuming, all you know is that you receive a single monthly bill. And that single monthly bill tells you maybe if your house is being efficient in some way, because you may compare with your neighbors. Your building may be certified by some type of standard. Maybe LEED is certifying your building. Maybe you have some energy auditors that came to your house and said that your building was efficient. But those are very punctual connotations. You don't have a real-time or an ongoing assessment of how your building is consuming energy. Compare that to what's happening with cars. So nowadays you can buy a car that gives you instantaneous miles per gallon. You already know, at least there are bodies of standards that tell you if this is a hybrid car, if it's fuel efficient or not, and you have ways to compare it against others, even though the price difference between the two is enormous. Right? So you're talking about things that are orders of magnitude apart in terms of price, but again, you don't know enough about the more expensive one to actually tell what it is, where is it that you're spending the energy. So I'd like to talk about that problem specifically of how to actually assess better and get better feedback about energy consumption. And I'm going to focus on three things. One, how to actually get information about appliance consumption. So instead of getting a single monthly bill, how can we actually get information about how much each load inside the home is consuming? Related to that, how do we integrate sensors that are already being put in place in buildings to achieve that goal? And lastly, because it's not foreseeable that people are going to try to configure each individual sensor and make sense of all the data by themselves, how do we do it automatically? And how do we configure and train systems to do this automatically? At the end, I'll talk about future work related to this, and I'll leave some time for discussion at the end. So first, I want to point out that there are other authors in terms of publications in this area that I've been collaborating with. All of them here are from Carnegie Mellon University, some faculty, and some students that I'm collaborating with. So this could be familiar to you guys. This is, on the right side, we see a monthly bill for Duquesne Light, which is the company that provides electricity to Pittsburgh, one of the companies. And if you imagine that that same bill would come from, for example, your grocery shopping, and you would only have a single number to which you would reduce how much you spend on groceries, you would probably have a very hard time to figure out where you should spend less, or should you buy red meat versus white meat. So that's what we're seeing right now in the electricity domain. And what we'd like to see is to have a sort of a disaggregated bill that tells you how much you're consuming by each type of load, each type of appliance. Now, in the whole U.S., if you try to convert or generate that pie chart by averaging all homes, this is the figure for 2005, you'll see very broad ideas here. So, for example, refrigerators consume about 12% on average in every home. Air conditioning is a little bit more, 20%. And all the other appliances and lighting constitute 52% of the bill. But this is these numbers that are here are very dependent on the specifics of the house you're living in, on the social status that you have, on your lifestyle, and on many other variables, specifically where that house is located. So if you really want to make use of a pie chart like this, you would need it to be tailored for your specific situation. And that's what we're looking for. So where are we right now in terms of getting that? Well, appliances themselves don't give you this information. There are some people that are, and some companies that are thinking about doing this, on giving you real-time information about how much each appliance consumes. You can still go to the plate rating and say, well, this consumes 30 amps and it's 120 volts, so I can tell you that when it's on, this is how much it consumes. But how do you figure out how long it's on every day, and how long it's on every week, and how long you use it for? So that's not there right now. You can, for example, install sensors on each individual outlet on your house. And these solutions for a typical home go anywhere from $5,000 to $30,000. And that's already available. But who's going to pay for that? And how are you going to get some return on the investment from that? You can also go a little bit more aggregated, and instead of looking for each individual outlet, just measure each individual circuit on your circuit panel. And that'll tell you on a combination of appliances how much they consume. And those solutions are a little bit less expensive because it's only one point install. But frankly, you can get monthly data for free. In some places in the US, you can get daily data for free. Here in Pittsburgh, Duquesne Light provides that. And you can install a real-time meter outside or inside your panel for the whole house for as little as $200. Now, there's a point to make here, which is even though the technology is going to decrease in price because of Moore's Law, that's not going to happen to labor. And so if you want to install these things on every outlet in your house, you're still going to have to find somebody to do that. And in some cases, there are some appliances that are wired directly, don't have an outlet, and so labor is going to be the problem here. So what we'd really like to do is to take the cheap side and combine it with other sources of information that are easy to obtain or even free, like, for example, whether or not you're at home based on your calendar, some motion sensors that are already in your house maybe, your thermostat setting, to produce the picture about how much you're consuming in real time per appliance, which is what we wanted to have at the end. So if you think about it, that's going from low-cost information to high-value information. And why would we want to do this? Well, besides the general energy conservation goal, there are other things that open up once you have this data. So for example, you can start to mine this data to understand patterns and to understand where consumption is leading, and maybe probably predicting how you can save energy because you have models of how people are consuming the data, consuming the energy. You could also utilize this information in a social context and, for example, provide the user with some kind of information about whether or not his refrigerator is consuming more or less than his friends' refrigerators or people around on his same network, on his same house level, on his same household size, and so on and so forth. Utilities are very interested in this data as well, mainly because from their perspective, what they'd like to do is to shave peaks, so peaks in demand, and to do so they have to predict and forecast what the energy consumption will be in the next day or so. And if they have better models of how energy is being consumed, they can better predict this. And lastly, there's also this contextual setting that you need to provide to consumers whenever they're buying new appliances. So if you were to buy a new refrigerator and you don't know how much your own refrigerator is consuming, making the cost-benefit analysis of whether or not it makes sense to invest in a new refrigerator is harder. So that's, again, one of the goals for why we want to do this. And I guess to further motivate this and to give you a sense of how difficult it would be to go from the very cheap solutions up to the disaggregated information, let's look at daily consumption for a typical house here in Pittsburgh. So on the red line, I'm showing the electricity used by day in kilowatt hours, and on the blue line, I'm showing the average temperature around that house for those same days. And you can see that there's an inverse correlation between the two, because as temperature drops here in Pittsburgh, people start to turn on their heaters, and that's what triggers the energy consumption to go up. So probably what you could say from this data is that at some point after maybe November 22, somebody turned on the heater. And you can see the heater from this data. If you look at, now let's look at once per minute samples instead of once per day. Now you can start to see other patterns. Like, for example, you can start to see this is on the very middle, you can see the nighttime because there's almost no consumption, and on the two ends you have the daytime. You can also start to see patterns of individual appliances cycling. So, for example, this could be the refrigerator turning on and off every so often, or maybe a water heater. So at this point, you can start to differentiate between appliances. And if you take this even a step further, and to prove the point, I'm just going to show for one specific appliance. This is a large coffee machine, one of those that you put coins and they spit out coffee or tea or different drinks. You can start to see the individual components within that appliance. And now I'm measuring, instead of once per minute, once per second. And what you can see here is that these repeating cycles are the heater keeping the water hot, which happen every so often, even when the appliance is not being used. But you can also see other blimps here, and these correspond to tea being dispensed. This one here corresponds to coffee, and this one here corresponds to mocha. And you can start to see that they have some individual characteristics that you can use to differentiate them. So I brought this a little bit further and took this concept to my whole house, for example. And what you can see here is that every time I turn on my kitchen light, now we're looking at, instead of once per second, we're looking at 60 hertz measurements, so 60 times a second. Every time I turn on my kitchen light, the power consumption of my house does something like this. And every time I turn on my refrigerator, it does something like this. So you start to see that there are individual fingerprints, let's call them, that identify individual appliances. And you can use this information to sort of understand what's happening in the whole house by just measuring from one single location. But there are challenges and solutions that are needed to be provided for doing this. I'm going to talk about them very briefly. Specifically, I'm going to talk about three things. One, this concept of that I just explained, which in the literature is called non-intrusive load monitoring, and which has been a topic of research for about 20 years. And I'm going to talk about what are the challenges that remain there and where we are on regards to getting that implemented in the real world. And then I'm going to talk about how do you integrate other sensor information. So for example, I talked about motion sensors, and I talked about your calendar, and I talked about your thermostat. How do you integrate that in a way that you can leverage them without having to make more efforts? And lastly, how do you automatically configure this so that it's easy for the users to use? So starting from the inexpensive appliance feedback. As I mentioned before, the non-intrusive load monitoring, which is NILM for short, is a topic that has been on the research community for about 20 or 25 years. And it consists of basically 5 steps. First, you acquire data, namely voltage and current for the whole house. Then you do event detection, which means I want to know when there's a change in these voltage and current signals. And I will relate those changes to appliances changing their state. Once I know that there has been a change, I extract some features around that change and try to use those features to classify what happened. Once you've classified what happened, which could be, for example, the TV turned on, then you can start to compute energy, because you are already collecting information about the power consumption, and you know what happened before and how much the power was after that event. And you can subtract the two and say, well, this difference corresponds to the TV, and so the TV must be consuming this much. The main 4 challenges that we identified with this area of research when we started working on it was basically that, first of all, you need to train the system. So what does training mean? Training means that if I install a prototype system in your house right now, I would have to go through the list of appliances that you have and teach the system that every one of these events corresponds to every one of these things. So the first time you install it, your TV turns on, the system says, well, I detected something, I don't know what it is. And you say, well, that was the TV turning on. Next time it sees that, it can identify that pattern with the TV. So this is, training is maybe a cumbersome process that we need to overcome in some way. And I'll talk about that in a few moments. Also, the problem is that nowadays, the appliances that exist inside a typical home are very different from those that existed 20 years ago. Not only in terms of how many, but also in terms of how many settings they have and how they operate. So that makes it a little bit more challenging. Also, the solutions that were provided so far have been not focused on the user. So most of the solutions provided in the early 80s and 90s were considering that the user had no involvement in these things, and the information that you were getting was mainly to be provided to the utilities. Whereas I believe that leveraging the users is probably a good idea because the user is the one who knows what's really happening in the home. So if the system is not confident, it should ask the user to supply some additional information. And lastly, the field hasn't been able to come up with ways to compare different algorithms and different solutions to the problem in a way that is objective. So right now there are many researchers working in this field, and everybody has their own performance metric to evaluate their algorithms. And there are no ways to understand which one is better or worse. So that's also a problem in terms of the research field. So very briefly, let me maybe stop here and see if there are any general questions. I'm going to start diving more into the details of non-intrusive load monitoring right now. If there are any quick questions, I'd be happy to answer them here.
We must have a shy group, Mario, because right now we don't have any questions. But if anyone does, please just use the tab on your toolkit.
There are going to be more situations like this where I'll stop, so don't be shy.
Okay.
So here what I'm showing is basically a block diagram of how we proceeded with implementing a non-intrusive load monitoring algorithm, just to give you an overview. So as I said before, you start with collecting electric power data, specifically voltage and current. You pre-process this, convert it into more traditional power metrics like real power, reactive power, and power factor. And then you do edge detection, which basically means you detect when there's a change in steady state. So it went from 20 watts to 100 watts. So that was probably something that happened there. You extract some features around that event, so maybe how that change happened, what the transient looked like, and you use those features to classify what happened. So this could be, as I said before, refrigerator turning from on to off. And that's what the result is. It's an appliance state transition, which is then checked with an appliance state model that keeps track of what appliances are doing and checks if that transition is possible, and shares that information with interested parties, which could be the users themselves, some database engines, the utilities, and it all relies on a signature database that has all the fingerprints of the individual appliances. So again, just to give you more context of how this happens, you install sensors just at the main panel. Specifically, if you're here in the US, you will install sensors on both faces. If it's a three-phase panel, you install sensors on each one of the faces, A, B, and C. If it's a split-phase panel like traditional residences here, you will have two phases, so A and B, and you measure voltage and current on both. If you go to your textbooks, if anybody remembers, you will see that they tell you that AC power is a very sinusoidal and very periodic waveform. So voltage and current are both very nice and clean, whereas in the reality, they're very different from that. So on the bottom here, I'm showing what they look like for one of the houses that we have implemented. Blue is voltage, which is sort of periodic and very constant, but the other two, white and red, are current. And they're not sinusoidal at all. So all the theory that you had about how to calculate real and reactive power is based on the assumption that you're looking at sinusoidal periodic signals. And once that is out of there, you have to use some sort of other methods to actually calculate the same quantities. And so without going into many of the details, I'll just tell you that what we use is we go to the spectral domain, we go to the, we do a Fourier transform, and we convert this all into the frequency domain. And on the frequency domain, so by measuring the frequencies of voltage and current, we can come up with quantities that look like power and reactive power. But we have now the addition of being able to tell the power at different frequency bands. And so, again, I can go into the details of this transformation, but in the interest of time, I'll just show you the result of doing this. You remember that I showed you that the refrigerator in my house was turning on as the top diagram right here. That's the power consumption. But now with the added benefit of doing this on the frequency domain, we can also see how the power consumption changes in other frequency bands. And these are the different harmonics. So we have the first harmonic, which is the 60 hertz signal, the one that you're looking at the top, is on the first line here. And every other line is the second, third, fourth, and so on. All the other harmonics. And in this spectrogram, you can see that there is information on the other harmonic power components as well when the refrigerator turns on. And this could help us identify the refrigerator even better. So the trick to doing this is that you use the information about when there's a change, and I'm showing here power changing over time. When there's a change from one steady state level to another steady state level, you get a specific transient that corresponds to the operation of that appliance. And in this case, for example, your capital B over here shows a refrigerator turning on. And this large spike corresponds to the compressor. Sorry about that. This corresponds to the compressor starting. And that's why there's an inrush current that provides this large spike. Is that noise coming up to you, Nicole?
Yeah, I thought maybe it was the compressor starting. No.
There seems to be some construction right next to me happening at this moment. So if it becomes really bad, I can move my computer to somewhere else. But if it's okay, I'll just keep on going.
Yeah, maybe just talk a little louder.
Will do. Will do. So once we know that there's a change and we can start detecting it, we can recognize appliances. But before we do that, we have to recognize when the changes happen. So we want to know what are these changes of steady state and when they happen before we know what they are. So to do that, we implement a very basic probabilistic algorithm that is called the generalized likelihood ratio, which compares the ratio between the probability of any single sample to belong to distributions of before and after the event. And after doing that, you can start to find out when there's a change in the mean or when there's a change in the steady state of the signal. So now we understand where these changes are occurring. After we detect when they occur, the next thing is what they are. And I'll show you here a little video of how the event detector is detecting them. On the very top screen of the screen, we see the voltage and the current, as I've shown you before. And the bottom two diagrams are the power on one face and on the other face. The very bottom here, on the far right bottom, you can see the event detector predicting where these events are happening. And it's sort of giving votes to where these things are happening. And it'll once the votes become more than a certain threshold, they're considered events. And so this is how the system performs in real time. So now after we detected the events, the next question is, what are they? And to do that, we sort of capture a window, a fixed window of samples around each event. And we do this on the real power, on the reactive power, and on all the harmonic components. And by doing that, we can start to teach the computer to represent this signal in a way that is easy for it to then compare it to others. So if you look, for example, at this specific red square right here, I'm showing it on both the real and the reactive power on face A and on face B. I do the same on each one of these faces, so I'm only going to focus on one of these transitions. What happens is that if you want to represent this for the computer to be able to interpret it, you can either use all samples. So for this, you would use the 100 samples that are here and each of the numbers that are here, and you would have a 100-dimensional vector. Maybe easier than that is to say, well, I'm only going to use how much the change was. What is the delta? What is the actual change between the average here and the average at the end? And that's one single number. Maybe what you want to do is you want to fit a line and use the slope and the offset of that line that you just fitted as the representation of this. Or maybe you want to fit another function that is nonlinear, and then you want to find out what are the coefficients to that function that you're fitting, and you store those coefficients. That's what we do at the end. We use a nonlinear function and we try to regress the transient that we just saw and store the coefficients of that regression. And we use the coefficients of regression to compare them against other regressed coefficients and see how well they match. And if they're close enough, we just call them a good match and label the newly detected event as using the same label as the other one that we had. And by doing that, the system can start to predict energy in total. So here you see the true power for the house as measured by a ground truth meter. And then sort of on the magenta line, the NILM predicted consumption, which shows that it follows nicely what's happening but at some point it starts to diverge. And this is mainly because it can miss some events, and if it does miss an event, then it will not know that for example, the TV turned off, and it will assume that the power consumption is the same as it was before the TV turned off, and it will accumulate that error over time. So now we're working on algorithms that try to minimize that error by treating it as an optimization function that has to abide to the measured power at every point in time. So that's just to give you an overview of how you go from acquiring the data to generating something that looks like the actual consumption. What are the remaining challenges? One of the main remaining challenges is that the event detector that we're using right now is detecting more events that we would like it to detect. So, and some of this may have to do with the way we define events, and some of it has to do with the actual algorithm. So for example, I'm showing here a microwave turning on, and you would assume that when you turn on a microwave, it's just one single thing that happens. Whereas in reality, there are maybe two things that you can distinguish from this graph. The first one right here is that the turntable and the light turn on. And it's only after a few brief moments that the magnetron, the actual magnetron that's going to be producing the microwaves, turns on. And that's the second jump right here. So the event detector says, well, I detected one right here, and I detected another one right after. And to the event detector, these are two distinct things. To us, it's only one. So we're looking at putting a layer on top of the event detector to actually try to combine these events into one and not have to deal with trying to label these two things as separate things. You could go down the path of saying, well, this is a hard drive inside a computer, and this is the fan inside a computer. And if you have to tell all these things to the system, then it would not make it feasible. And users would probably not want to use it. Also, if you look at the overall performance, this is how it tracked over the course of a few hours the refrigerator consumption in my house. You can start to see here that, on the yellow line is what it predicted, and the background gray area is what it actually consumed. It does a pretty good job, except for example, places like at almost 6 a.m. when, if you look at this, the refrigerator went up by a lot more than it usually goes to. And I don't know if anybody here in the audience know what this could be. And if you do, please just comment really quickly. But I'll tell you that what this is it's basically an event that happens every 12 hours or so on your refrigerator, depending on your settings, and it's a defrost cycle. And it's something that you cannot necessarily train when you start the system because it happens sporadically. You don't necessarily have the chance to catch it. And since we didn't in this house, the system didn't understand what that was and thought that the fridge was still on. And it kept it on. And then when it saw that it actually turned on again, it assumed that that was a misclassification and it should have been off. So it took another 2 cycles to actually cut up again and again start predicting what it should be predicting. So this brings up the question of the importance of training the system and how you actually do this in a way that's reliable and doesn't necessarily rely completely on the user. And to that extent, one of the first questions I've been working on is trying to find out if there are ways to generalize signatures of appliances. So is the signature of one refrigerator of one particular brand similar to the signature of another refrigerator of another brand, and so on and so forth? Can we actually generate models that are general enough to predict all refrigerators? And if we do that, we could actually deploy systems that don't need to be trained on, let's say, refrigerators. And can we do this for other appliances? The other question I have is how do we leverage information from other sources? And I'm going to talk about that in the next few slides as well, very quickly, so that you can generate a better solution to the problem without having to rely on the user. So if you know, for example, that there was motion in the kitchen, then the next event that happens is more likely to come from a kitchen appliance than from a bathroom appliance. So how do you incorporate that? And lastly, how do you compare between the performance of different algorithms? And this is a topic that I will not address in this talk, but it is a very important topic for the whole research community in this area. So again, talking about how to generalize signatures. I tried doing this by taking a number of different refrigerators from different brands, a number of different microwaves, and a number of different compact fluorescent lights, and use these 3 appliance types to try to come up with generalized models. And without talking about all of the details, I'll just show you 2 screenshots that summarize what I did. If you look at here, I'm showing the turn on of all refrigerators that I collected, and these are the transients. These are the fingerprints of them. You can start to see that they fall into a very general pattern. So they have all a spike because they're all compressor based, and then they settle into a steady state. So we are already doing this in other domains. If you think about it, today you can turn on your camera, point it at any given area where there's a face, and it'll start detecting where those faces are. It's true that every face is different, but this camera can detect sort of a generalized model of a face. And I actually implemented the same approach that they're using to do face detection, or that they used at least in the beginning, to do appliance detection on these signatures that I'm seeing here. And so what you can see is that I can now go through a whole set of a whole data set and tell the system, well, tell me where on this whole data set are refrigerators turning on or refrigerators turning off. And it'll start detecting those. And the way it does that is it tries to compute a matching function between a pattern that it has stored, which is the general model, and the sort of the figure that you're seeing on the top, which you could think of it as an image in the same way that you can think of detecting faces in an image. And it'll start to do that and detect where the pattern matches best. Again, I don't want to go into the math of how you do that, but it's a dot product between 2 vectors, 2 normalized vectors. And because it's doing a dot product between 2 normalized vectors, their dot product should be 1 if they're exactly the same. Their angle should be 1 if they're exactly the same, or they should be 0 if it's exactly different. So what you can see here on the theta here is the result of that dot product. And if it's almost 1, it would be perfect. So if for the microwave off and microwave on, you start to see very good performance. But for the CFLs, for the compact fluorescent lights, we saw very bad performance. And we hypothesized that this is because the CFLs are very similar to many other appliances that are in the house. So for example, you have incandescent lights that are very small. You have small appliances that are very composed of many electronics that very much resemble CFLs, and so on and so forth. So that's one of the challenges there. So maybe for large appliances we can generalize this. How do we combine data from other sensors? And maybe this is a good time again to stop it in case there are any general questions. Nope.
Still no questions, Mario. So.
Okay. That's fine. I mean, maybe I'm doing a great job. I don't think that's the case, but
no maybe about it. I think that's exactly the case.
Okay.
So.
Okay. Well, we'll leave the questions to the end. That's when I'm almost there at the end, so I'll leave I'll open for questions again at the end. And so again, going back to the question of how do you integrate other sources of information to improve the solution to this problem, I started working on the issues regarding interoperability and sensor integration. And I asked myself, for example, this specific question. Can we use information about the motion in different parts of the house to predict what is more likely to happen and feed this into the system so that it doesn't confuse itself so often? So if there was motion in the kitchen, as I said before, and there's an event, it's more likely to be a kettle or a microwave than it is to be a hairdryer or than it is to be an iron, for example. And I instrumented a few homes in this using this setup where I had environmental sensors. These are hobo sensors, off-the-shelf sensors, motion sensors, and by environmental, I should say that I mean using light intensity, humidity, temperature, sound level, and acceleration. I also had plug transducers which measured individual plugs so that I could verify the predictions of the system. And I had a whole suite of different interaction points or interfaces. Some were mobile, some were over the web, and so on and so forth. So basically what you would call an intelligent home, we deployed a few of these across Pittsburgh to understand the problem. And this is just looking at what the web interface would look like. You would be able to see what each of your appliances were consuming and how much over the past month, and see a pie chart. And the same thing with the sensors in different rooms, and the information about light intensity and so on and so forth. So you could access this over the web. And some of the things that I discovered were quite interesting. So for example, if I decided that I wanted to plot the power consumption of my house, and at the same time plot the audio level in my living room, you would start to see that there's a direct correlation between audio level increase and the air blower, which is when I turn on my air conditioner. It's central AC, but when I turn it on, the air blower turns on, and it produces an increase in the audio level, which now that if I think about it, it's pretty obvious, but it wasn't obvious to me from the beginning that this would be a good source of information to tell whether or not the AC was on. And so I did some experiments with the audio level sensor, trying to do different things in my house to see if it was only when I was turning the air blower, or if it's also when I was trying to talk or playing guitar or doing different things. And you can start to see there's a little bit of a characteristic to this air blower going on. The same thing would happen, and this is a lot more obvious. This is something I knew was going to happen. When you turn on the light in the bathroom, you see a light level increase, and you also see that there's an increase in the power. Now, what's interesting about this is that if you teach the system that there's a correlation between these two things, you can go ahead and switch the light the light bulb in your bathroom to something else, maybe a CFL, maybe another wattage light bulb of the same kind. And even though the signature in the power will be different, since it knows that this is very correlated with the light intensity in the bathroom, then it can start to retrain itself automatically. And the automatically is the keyword here. We want to achieve something that doesn't need the user to actually tell where the sensors are, what are the correlations between the sensors, what this appliance is, and so on and so forth. And one of the things that I've been working on lately is trying to use this information in an unsupervised fashion and trying to come up with correlations between things that the system can use automatically. To give you an example of that, here I'm showing after a week of data collection, I ran a correlation matrix on all of the signals that I was getting and tried to find significant correlations. And here I'm showing those that have a very high correlation coefficient and a very low p-value, which means that it's a very likely correlation. So for example, the bathroom light and the bathroom motion, obviously, they're correlated. The bedroom lamp and the bedroom motion, obviously correlated. Sort of less intuitive, you have the, let's see which one. The kitchen motion and the living room motion are correlated. And that is only because the kitchen and the living room are next to each other in my house. So you can even start to see that this represents correlations on the temporal space and also on the space itself. There are spatial correlations here. So I use that information to tell the system, well, now that you know what things are correlated with motion, try to tell me if I am doing very bad on some things. So for example, if I'm wasting energy, because normally on the top here, the living room motion is very correlated with the TV, the living room light, and the sound system. So it knows that these things are correlated, which means that when I'm moving around the living room, I'm usually using these things. But if I'm not moving around the living room and these things are consuming, then alert me, please. I probably fell asleep in the living room, or I probably am out of the living room and left the TV on. The same thing can be done with any sort of correlation that the system detects automatically. And these sort of, mining information without involving the user and just letting the user know about the high-level decisions is where I think most of the innovative approaches are going to come up after we enable the information from each appliance to be available to everyone. Other things that I'm working on are trying to find ways to automatically train the system. And here I'm showing a EMF sensor, an electromagnetic field sensor, that you can quickly deploy around your house, put it next to the appliance, and it'll detect changes in the electromagnetic field and transmit those changes back to the original system and tell it, well, this was the refrigerator because I'm next to the refrigerator, and it just turned on, it just turned off, it just turned on. It'll start training the system automatically. So you can deploy these things that are very cheap, probably $1 each, put it next to the appliance, and collect data for a week, let it there to train itself, and then return these back to the manufacturer or back to the service company that's providing them to you. And I'm not going to go into the details of how the EMF sensor works, but I can answer questions about it later. So again, I'm wrapping up here. I'm going to want to finish with some of the future work that I see in this area. Specifically, I think one of the first things we need to find out is what can we do with smart meter data. Right now I was working with data that was sampled at a very fast rate. I was using custom hardware to collect this data. But what can we do with the sensors and the monitoring systems that we already have in place? And this is an interesting question that I think somebody should be paying attention to. Also, this problem is very similar to the problem of speech recognition. If you think about it, we're analyzing a signal and trying to detect where the words start, so where the appliances turn on and off, and what these words are, so what these appliances are. And I haven't seen anybody working on this specific question, and I think it's a very interesting one, how to leverage sort of tools from that area and apply them here. Also, I think I've been mostly talking about the things that are happening from the meter down. So what are the appliances doing? But there's a lot of communication that needs to happen between the utilities and the transmissions and the distribution systems and the appliances themselves to sort of optimize the grid as a whole. And how to affect behavior and how to influence people to change their actions using this information is also another topic of interest. Maybe one last one is now that we have this data, we could do automated continuous commissioning and find out when it's good time to replace these appliances or these big loads, when they're failing, when it's good to contact maintenance and try to repair them. And you can start to do this not only on the electricity, but there are people already working on using this same technique of non-intrusive load monitoring for water consumption and also for gas consumption. So you can see this as a resource monitoring tool for understanding where resources is going and the different types of consumption inside the home. Lastly, you'd like to have this work on a distributed fashion so that if you, for example, train one appliance in your house, a refrigerator, then somebody else should not have to train that same appliance. So it would be nice if you could have information coming from all the systems that you have deployed into the cloud, let's say, and using this information to sort of improve the system in a distributed fashion. Lastly, I'd like to thank my sponsors, Bosch, the automotive and appliance manufacturer company, and NSF for providing me support for this, and I'll open for questions.
Thank you very much, Mario. I currently don't have any questions. I think we might have one person who's trying to write this through chat. There is a question section on your toolbar, so if you can type in there, that will get the question to me. I had a question. We had a presentation at a FIATech conference a couple years ago from Google, I guess, and I think it's their Homes initiative. Do you know anything about that, and do you have any predictions as far as when some of this technology might be available to consumers?
That's a very good question. I don't know how much I'm allowed to say. I'll basically say that I predict that this is probably going to take place in the sense that you're going to see applications using Android for the home within the next year or two. And I see this as a great step forward from a big company into the domain that I'm working on. And I think the more you see people doing this, and especially big companies, the more other players will start to pop up. And specifically in the way that Google is doing this, which is instead of focusing on one specific application or instead of focusing on one specific hardware, they're just providing the layer that allows for this ecosystem to grow. And I think that's the key point there. A lot of people are doing this in very different ways, and most of the solutions that are out there for home automation or building automation or all of that are very proprietary, and you have to buy everything within a very enclosed ecosystem. Whereas Google is trying to jump out of that and trying to enable others to come into the game and use their sort of middleware layer to start working in this area. So I think it's a very exciting opportunity, and there's going to be a lot happening in the next few years.
Okay, thank you. We have a couple more questions. When you said training the appliance, do you use the monitoring data to train ANN?
I'm sorry, the last thing, ANN?
ANN.
Oh, the artificial neural networks. So we've tried using artificial neural networks, and they are successful to some extent, but not necessarily more or less successful in other methods. So currently, we're using a very simplistic approach. We're using the k-nearest neighbors algorithm, which is basically looking at the Euclidean distance between all the different signatures that we have and the one that you just detected, and finding the closest one. So that means you have a database of all the signatures, and you get a new one, but you don't know what it is. You find the distance of this new one and all the other ones that you have in the database, and find the closest one. The label of that closest one is the one that you will use for the new one. That was actually a lot better than using neural networks or using support vector machines or using decision trees and so on and so forth.
Thank you. Someone's curious, what is the timeline for this kind of experiments, and can you scale it from domestic household to a commercial setup like schools?
Okay. So can I ask a clarifying question? When they say timeline, is that timeline for making this available commercially, or is that timeline to just use it at different places on a research setting? I'll answer the second part of the question while they reply to you. And the second part of the question is, can you scale it up to commercial buildings like schools or other larger buildings? And the easy answer is yes, but there are challenges to doing this. One way in which you could do it and still remain using the same technology that we've developed is to sort of divide the whole commercial building into different sections by just measuring individual circuit panels. Because in a typical home, you'll have one circuit panel that feeds probably 40 circuits, and at that level, you have enough complexity that the system will work okay. But if you add a lot more appliances and a lot more circuits at the same time, then you'll start to complicate the problem a lot more, and it's going to be harder for you to actually differentiate between one appliance and the other. One, because they may be overlapping in time. You'll have 2 or 3 things happening at the same time because you have so many things. And second, because the appliances that are in these types of buildings are different than the ones that are in the home and are a little bit more complicated. So if you think about big AC systems, big air conditioning systems, or some variable speed drives that they have, these are very complex loads that require a little bit of modification to the technology that we've been developing so far. So the answer is yes, but there's some work to do to get there.
Okay, and he did respond and say, how long does the research take at the testbed level?
Oh, so to implement.
Right.
Yeah, so I can go into a house and get the system set up and trained in about 2 or 3 hours. I suppose that if we speed up the process and we actually make this a little bit more towards the end user acceptance level, we could reduce that to maybe 1.5 hours. But still, I think for consumers to adopt this, 1.5 hours is not good. Nobody's going to spend 1.5 hours to set up this thing on every appliance in their house. So going through all appliances, switching them on and off. I think we need to develop technology that actually works out of the box, and that's what we're shooting for.
Thanks. I have one more question. Again, FIATech is focused a lot on the capital projects industry, so this one speaks to that. And regarding capturing energy uses for both buildings and plants, is there a definition or a list of new design and construction data that is required or would be required in order to implement that in the sector?
That's a very good question. So I guess there are many ways to answer that question. One thing that I would encourage, if somebody is thinking about implementing a system like this in a new building, there are things that could be done to the electricity distribution system, to the way you are grouping things together at the circuit level that could improve what we're doing here and could make it a lot easier. So for example, if you focused on just having large loads be monitored in one single circuit, and if you could focus on grouping lights into one type of circuit and grouping appliances of the same type into individual circuits, then you can make the problem a lot easier, because now you have a sense of what to expect before you start trying to understand what the data is saying to you. So in that sense, I think working with the electrician who's designing the electric distribution system is a key element there. Then there are other elements that could be interesting, and I think especially during the design phase, if you are thinking about implementing a system like this, you may want to include other sensors inside the house or inside the building or the large facility that you're instrumenting, and sort of place these sensors and use the sensors that are key to solving the problems that this system alone can't solve. And those are, for example, large variable speed drives on air conditioning systems which change over time and don't have specific transients. If you can instrument that separately, or if you could at least have a building automation system that tells you when this thing is on or off, then I can start subtracting that information from the overall power and give you a better idea of what the rest of the loads are doing. So there are some things that could be done in advance if you wanted to implement something like this. And those are just two. I don't know if that answered the full question, so I'll let them respond if they want more.
Okay, and we have one last question. We have 2 minutes left. Have you thought of leveraging the use of smartphones, for example, for energy literacy, through providing intelligent feedback to the occupant? I believe this may affect user behavior.
Yeah, that's a very good question. And in fact, I've been working with colleagues in the Human-Computer Interaction Institute here at Carnegie Mellon and elsewhere, where that becomes their central goal. So I'm focused right now on providing the information and making the information available. How we use that information to provide feedback, I think, is a very important question. I'm not actively seeking that, but I can tell you a few examples of what I've been using so far. So smartphones, I think, are interesting in two ways. One, because they may help you train the system. You may not be in front of the computer, in front of the device when something happens, so using a smartphone is sort of the obvious choice. Also because normally, and I think I've seen some studies that back this up, if you provide feedback on the moment that something is happening and on the context that something is happening right then, it's more effective than if you provide it later. So for example, receiving information at the end of the month that you were using your oven in a wrong way is not as useful as receiving that feedback right when you're turning on the oven. That's when you're actually more likely to change your behavior. So smartphones are the best way to capture that. And to that extent, I've been working with a couple of students here to try to implement ways to use smartphones to access data from different meters that are already installed in the building, so that you can use the smartphone to say, well, I'm here in, let's say, CMU building X, and I want to know what the consumption is right now. And you can just click, and it'll access all the meters that are close to it, add them up, and give you a value saying, well, the consumption value is 800 watts. And this, contextualized information is what I think is more effective, and that's why smartphones are the way to go in that sense. So I don't know if I answered the question or if I basically just corroborated with your statement, but I think that's the way to go.
Okay, well, thank you very much. We have reached, I guess, the conclusion of our hour. I want to just remind everyone that we have recorded this, and we'll be making it available on the FIATech website at fiatech.org within the next few days. Give us a couple days to package it and post it. And I just want to thank you again, Mario, for sharing your work with us. And I hope everyone will be able to join us, not next week, we'll be taking next week off, but the following week we'll be having a members-only webinar during this time slot. So thanks again, Mario, and thanks everyone, and have a great day.
Thank you.